Hello students, I am Ahanab Hamid Abid. Our today's lecture is on p-n junction formation. Before know about p-n junction formation, we have to know about the valence band first. Valence band refers to the energy level that holds the outermost electron. In the figure, we can see that in the outermost there are four electrons, which is called valence electrons, and the energy level of these valence electrons are called valence band energy level. On the other hand, when the electrons are free to move, they contain in energy level, and this energy level is called the conduction band energy level, where the electrons are totally free to move. The difference between valence band and conduction band is known as the band gap. In case of insulator, the band gap energy is very much high, so only a few electrons can move from valence band to a conduction band. On the other hand, in case of semiconductor, there is a moderate level of band gap, so few electrons can move from conduction band to valence band to conduction band. And finally, in the conductors, the valence band and conduction band is totally overlap. So a lot of electrons, almost all the electrons are free to move. Okay. Now n-type semiconductor. When a semiconductor is doped with pentavalent atoms like phosphorus, arsenic, or antimony, then it is called n-type dope semiconductor. In the figure, you can see that a silicon crystal is doped with antimony. The antimony have high valence electrons, and four of them make a covalent bond with four silicons. So it has three electrons. In this way, after adding some antimony with intrinsic silicon, we can make it as n-type semiconductors. So the majority charge carriers in n-type semiconductors are electrons, and the minority charge carrier here is holes. Another type of semiconductor is called p-type semiconductor, where they are doped with trivalent elements like boron, aluminum, and gallium. In the figure, you can see that the silicon crystal is doped with boron. As boron has three valence electrons, when it try to make a covalent bond with silicon atoms, a hole is produced due to the missing electrons. As a result, the majority charge carriers in p-type semiconductors are holes, and minority charge carriers are electrons. Yet, two important phenomena to learn about the p-n junction. The first one is diffusion. Diffusion means the flow of electrons or holes from high concentration to low concentration. Due to concentration gradient, electrons move from high concentration to low concentration. On the other hand, deep velocity means the movement of electrons due to the potential from low potential to high potential. Okay. Now in the figure, we can see that the right part of a silicon crystal is doped with n-type material, so it turns into n region. On the other hand, on the left side of the silicon crystal doped with p-type semiconductor, so it's now p region. In the n region, there is a lot of free electrons than the p region. So the free electrons from p region try to flow from n region to p region due to concentration gradient. After some time, as the n-type region lose some electrons, it turns into a positive terminal. On the other hand, after getting some electrons, the p region turns into negative terminal, and due to the presence of positive and negative terminal, a potential is developed between them, which is called the Bettier potential. When the potential gets enough energy to resist the electrons, no current flows from one region to another region. In this way, the p-n junction forms when the drift and diffusion velocity get equal values. To get better understanding, let's move the next image. In this image, we can see that the conduction band of p-type is presented at higher level than the n-type. Okay, I will explain it later why this happens. But in this figure, we can see that the conduction band, upper conduction band of n-type is close to lower conduction band of p-type. That's why the electrons from upper conduction band of n-type easily move to the lower conduction band of p-type from here to here, from here to here, from here to here. Due to this movement, there is no electron present in the upper conduction band of n-type, and this turn into this image. So here is no electrons present. So a potential gradient is developed, and this potential is called the barrier potential. Okay, and we know that the band gap is totally constant. That's why the valence band also goes down. As a result, a potential is developed. Okay. Now let's turn to Fermi level. Fermi level is the energy level where there is a 50% chance of finding an electron at room temperature. In case of increasing conductor, it stays as the middle level, because at the middle level there is 50% chance of finding electrons. However, in case of n-type material, the Fermi level goes to close to the conduction band, because in n-type semiconductors there are a lot of free electrons, so they need only a few energy to go to the conduction band. As a result, the donor level is very much close to conduction band. On the other hand, in case of p-type material, the Fermi level is close to acceptor level, because there is so many holes present in the valence band, and the electrons prefer to go in the valence band. So the chance of finding electrons is close to the valence band. So we can see that there is a gap between the Fermi level of n-type and p-type. When junction produce, the both of the Fermi level comes into equal level. When they come into equal level, a junction is produced. And here you can see that when both of them come into equal level, a potential gradient is produced. And this potential is called the band gap. This potential is called the barrier potential. And in this way, p-n junction is produced. Thank you for attending this class. Today is no more. Thank you. Stop, please.